Let's explore a bit more about this idea of confidence intervals and a trade-off for a given sample size. For a given sample size, there is in fact a trade-off. In fact, we have the following trade-off. A higher confidence level, right, so 99% versus 95%, it's going to give us more certainty that the true population parameter is somewhere in our interval estimate. With a 99% confidence interval, we're 99% confident that the true population parameter lies within our interval estimate. With an 80% confidence interval, we're only 80% confident that that true population parameter is somewhere in our interval estimate. So in general, you might think, well, with a higher level of confidence, that's desirable because we're more confident that our interval estimate is going to capture that unknown true population parameter. The problem is that with a higher level of certainty, with a higher level of confidence, there comes a wider interval estimate. So a 99% confidence interval, you're multiplying the standard error by 2.58. Whereas with a 95% confidence interval, you're multiplying the standard error by 1.96. That larger value of z star, right, that's going to create a wider interval estimate. And with a wider interval, it may not be substantively meaningful. I'm 99% confident that most people who are listening to this lecture are between 0 and 98 million miles away from where I'm giving this lecture on the Harvard campus. So the key point is that a very wide interval with a very high level of confidence, that the width of the interval, it may be too wide to be actually substantively meaningful. So just to recap, the formula for the confidence interval of a mean is our point estimate, x bar, plus or minus z star, times the standard error. And that confidence level, right, it's going to affect how we set z star. With a higher level of confidence, that value of z star is going to be higher, because we want to capture more of those sample means around that population mean on the sampling distribution. And with a lower confidence level, we want a lower value of z star. And so when we multiply that standard error by a higher value of z star, that interval is just going to be wider. It's going to inflate or get smaller based on our level of confidence. So let's look actually what happens when we change the level of confidence using a couple of possible scenarios. So in this case, we're just collecting a bunch of sample means. Each time we calculate a point estimate and calculate z star times the standard error. So in this case, the population mean is 0. So mu is 0. That's given by that horizontal line. And you can see here we have a bunch of confidence intervals, each based on a sample size of 25 respondents. These are 99% confidence intervals. And we expect roughly 99% of those intervals to contain the true population parameter. Now, in matter of fact, depending on, it's possible 100% of those intervals will contain the true population parameter, maybe 98%. The idea of confidence is if we collect lots and lots and lots of these samples, calculate a point estimate, a plus or minus z star times the standard error, the idea is that we expect 99% of them too. So in this particular scenario, all of these interval estimates contain the true population parameter. But the key point is that we expect about 99% of these to contain the true population parameter. These intervals are pretty wide here, right? It's either bouncing around, but they all include that horizontal line, which represents the population mean mu of 0. Now, if we have a 95% confidence interval, we're going to be 95% confident that these intervals will contain the true population parameter. So in practice, if you repeat this process of calculating these point estimates plus or minus 1.96 times the standard error, you can see the intervals are a little bit smaller in this case, right? But sometimes those red intervals are those that do not contain the true population mean mu. So we're going to get some intervals that don't contain the true population parameter. But we're confident that we'd expect about 95% of them too for any given set of interval estimates. With an 80% confidence interval, you can see those intervals are smaller. Right? Any particular interval, it's smaller. That's just a reflection of the fact that that value of z star is now smaller. The problem is that you can see that we'd expect to have, if you collect 100 sample means and with 100 interval estimates based on those different samples, you'd expect about 20 out of those 100 not to contain the true population parameter. And you can see here, those red interval estimates, those don't contain the true population mean. Right? With a 50% confidence interval, those intervals are even smaller. Right? That's just because our value of z star is smaller. The problem is that roughly half of these intervals are not going to contain the true population parameter, and another half will contain the true population parameter. So that's a pretty low level of confidence, but the trade-off is that, in fact, the intervals are actually much smaller. So you can see that we have this direct trade-off. With a higher level of confidence, we have wider intervals, so wider for a given sample size. And so those wider intervals, they're more likely to contain the true population parameter. We're more confident that they will include the true population parameter. But with a lower level of confidence, we're less confident that those intervals will contain the true population parameter, but those intervals are smaller. Right? So there's this direct drawback, and this kind of revealed in this Garfield cartoon. The point is that a really wide interval, right, a really wide interval, which is associated with a high level of confidence, right, that interval may be too wide to be substantively meaningful. Again, I'm 99% confident that most people listening to this lecture are within 0 to 98 or 99 million miles away from where I'm giving this lecture, which is on the Harvard University campus. But you might say, okay, how can we kind of deal with this drawback between a high level of confidence, right, and the width of the interval? Well, let's see what happens when we increase the sample size used to calculate a particular set of confidence intervals. So far, we've been using a sample size of 25. But what happens if we use a larger sample size? Well, here we have 95% confidence intervals, but we increase the sample size from 5 to 25. So at the bottom, we have a confidence interval in which each interval estimate, and accordingly each point estimate, it's based on a sample size of 5. So we gather a group of 5 people from a population, calculate their sample average, calculate 1.96 times the standard error, and we plot a bunch of these confidence intervals from the same population, same sample size. And we can see that the intervals are pretty large, right? But using the same level of confidence and just increasing that sample size from 5 to 25, you can see those intervals get smaller. Right? This is just a reflection of the fact that the standard error is sigma divided by the square root of n. Right? The confidence interval is our point estimate plus or minus z star times our standard error, and our standard error is sigma divided by the square root of n. So with a larger sample size, right, that standard error is in fact going to be smaller. So one way to get around this sort of drawback of having a high level of confidence in a wider interval is to increase the sample size so that you can have a higher level of confidence, and that smaller interval will result with that larger sample size. So let's see what happens if we compare a sample size of 25 with a sample size of 250. Those intervals get even smaller. Right? Again, a larger sample size helps us deal with this drawback. So in sum, we have this drawback of a confidence interval. Right? On the one hand, with a higher level, for a given sample size, a higher level of confidence will produce a wider interval. A lower confidence level will produce a narrower interval. The problem is we often want a high level of confidence. We want to say, I'm 99% confident that the true population parameter lies within this interval. But if you have a really wide interval, right, it might extend way beyond the range of the data, so it's not that substantively meaningful. So the solution is to collect a larger sample size. So with a larger sample size, the standard deviation of the sampling distribution, that standard error of the sample mean, is going to be smaller. And accordingly, for a given level of confidence, our interval estimate, our confidence interval, will be smaller. And so in general, this should make sense because when we have more information, when we have a larger sample size, we can be more confident about a particular interval estimate in relationship to a population parameter.